Uh, we are very glad to have Georg Raffelt as today's lecturer. He'll talk about very interesting topic, stars as particle physics laboratories, old ideas and new developments. Please start.
So thank you very much for the invitation to talk about this topic that has kept me busy for much of my scientific career, which is how we can use stars to learn something about elementary particles and beyond the standard model particle physics. We'll talk about various topics which are indicated above here, but we'll go through it in the course of the lecture. So as you all know, we have in particle physics, we study the universe over many scales, right, ranging from the Hubble scale all the way to the Planck mass and everything in between. But the elementary particles that we know live somewhere in the middle in this mega electron to 100 GeV range, and below and above we don't know all that much. There's a high energy frontier which is studied, for example, by accelerators at CERN, especially. But on the other hand, we have the low energy frontier where neutrinos live, and other BSM particles may be existing. In particular, there are of course neutrinos, but in particular, and especially recently, people have studied many different low energy particles such as axions and their friends, as I call them, dark photons, fuzzy dark matter, neophilic bosons, all sorts of bosonic low mass objects, which are often called feebly interacting particles, and which have become very popular recently. And you can look up some of the details at this report of the CERN workshop on these FIPs, so feebly interacting particles. So this is what we're talking about: low mass particles that may or may not exist as an extension of the standard model. The heaviest particles that may play a role in astrophysics are possibly muons that exist in supernova cores and neutron stars, but this is about the highest mass that one can consider. Everything else is lower mass. So that's the kind of particles we are talking about in this lecture, and for which stars can be interesting. Now, just because I said old ideas, to make a connection to the history, the ideas go back a long time. In the 1960s, first it was acknowledged that neutrinos first of all existed and would be emitted from stars. And even early on in this paper, in the early paper, these authors argued that one could learn about neutrino electromagnetic properties by considering the excessive stellar energy loss by neutrinos, which would be enabled by the neutrino magnetic dipole moment. Another classic is this paper by Krylov and Pontecorvo, who proposed in 1969 already, when the solar neutrinos had just been measured and were seen to be a little bit deficient. There were too few solar neutrinos compared to predictions. And they proposed that this could be explained by flavor conversion. And this, of course, the explanation that in the end was the correct explanation. This was a very forward-looking paper and a real classic. So the first indication of BSM physics, if you like, neutrino flavor oscillations came from solar neutrinos and was first proposed by these authors. Later in 1978, the Weinberg-Wilczek axion was proposed as a consequence of the Pichet-Quinn mechanism to solve the strong CT problem, and many groups of authors said, well, if there's a new particle such as the Weinberg-Wilczek axion with a mass of a few hundred keV or MeV or something like that, and they said, well, that can be emitted from some stars and would feed back on stellar evolution. So they argued that we can learn about these particles from stellar evolution, and that's been the starting point. And ever since, many particles have been considered in many stars. And so that's the starting point of the ideas that stars are factories for low mass new particles, and therefore we can learn something about the particles from stars. So what kind of stars exist in the first place? In the audience, probably people know more about particles than about stars. So let me explain what kind of stars we will be talking about and what they are. So a star may form from molecular cloud or a cloud of dust, and then condense into a star, which could be small or a big star, where the borderline is something about 8 times the solar mass. So a small star goes through its burning cycles, eventually forms a red giant, and then sheds a lot of its envelope. It becomes something like what's called a planetary nebula, which sheds through this large luminosity. It evaporates much of its envelope, and what remains is this planetary nebula, this shining object which disperses into space. And then what remains is a white dwarf, a very small, the core of the thing, about half a solar mass and the size of the Earth. So that's a compact remnant called a white dwarf. And then, of course, the remaining material goes back into the fuel cycle and forms new stars. And there's this whole cycle of nucleosynthesis affecting the stars. On the other hand, if the star is more massive, again, it goes through its burning cycles, becomes a red supergiant, it eventually collapses inside, and leading to a core collapse supernova explosion. And then what remains is, instead of a white dwarf, a neutron star with a mass of around a solar mass, about 10 kilometer size, so the size of a city, maybe. And or in some cases, it will collapse to a black hole, maybe in 25% of all cases. The exact branching ratio is not known, but maybe something like that. And then forms a black hole, a stellar mass black hole. So that's the kind of objects we are talking about here. So the surface temperatures of these objects are maybe a few electron volts, so more or less visible, shine more or less in the visible regime, and inside they may have temperature of 1 to 100 keV. So this is really low energy, except for neutron stars that may have surface temperatures of keV, X-rays, and nuclear density inside, or supernova inside may have 30 MeV temperature. So putting it all together, we're talking about low energy physics, at most nuclear energy physics, but not, of course, high energy physics. So we are only interested here in low mass particles in the low energy frontier of particle physics. Now, the arguments that have been proposed are multifold, and I'm not going into all of them. One has used the sun as a source for particles. One has considered the lifetime of red giants or the brightest red giants, all sorts of arguments about white dwarfs, neutron stars, supernova, and so on. We go through a number of these arguments. One thing that I will not discuss here is the issue of superradiance of black holes. I think you had a lecture on these topics a few weeks ago, and I'm anyway not an expert on that topic. So I'm not really touching on black holes because I think you've heard about them before. Okay, let's first talk about the sun as a particle source. I mean, of course, the sun is a well-known source of neutrinos, and it was, after all, good for two Nobel Prizes for the discovery of solar neutrinos in the first place, then for solar neutrino oscillations in 2015. And today it's still good as a source for solar axions, and I'll talk about this briefly. Moreover, recently there was a lot of excitement in 1.5 years ago or so, where the Cno research has this excess signal that some attribute maybe to solar axions. So whatever this signal may do, it is not due to solar axions, because the other limits are much stronger and would not allow for this to be true. So whatever the solution to this problem, it is not solar axions. But so I'm just listing it here, but not going into it into any more detail. So let me talk a little bit about solar neutrinos, because there has been some excitement about this recently. So the sun produces neutrinos through nuclear reaction chains. So mostly the sun produces energy through the fusion of hydrogen to helium, which amounts to 4 protons, 2 electrons, become a helium nucleus plus energy. And most of the energy is carried away by neutrinos. So for each helium nucleus, we get 2 neutrinos. And so the sun radiates about 98% of its energy in photons and 2% in neutrinos, which means at Earth we have about 66 billion neutrinos from the sun per square centimeter and second. Now these production rates go through several burning cycles. The hydrogen fusion goes through, we have this pp1 chain where hydrogen protons are fused to form deuterium, then go through some stages and form ultimately helium. Or it can go through the Cno cycle, where carbon, nitrogen, oxygen acquire a proton, and another proton goes around and finally emits a helium nucleus in a catalytic way. So the carbon, nitrogen, oxygen remains the same. It has only a catalytic function. So the Cno cycle depends on the amount of carbon, nitrogen, oxygen in the sun, the so-called metallicity, and the temperature. It's very temperature dependent. So in the sun, mostly these pp neutrinos are the dominant source. The pp are the dominant source of energy of neutrinos, whereas in hotter stars, the Cno cycle takes over, but has never been directly measured. Here's an example of the well-known spectrum of solar neutrinos, where one can see as a function of energy, at the very lowest energy, one has these pp neutrinos from the proton-proton fusion, all the way to the boron neutrinos with the highest energies. And all of these blue sources have been measured precisely. So the uncertainty on the plot is so small now, combining theory and measurements, that you couldn't be even shown within the line width of these lines. On the other hand, the Cno fluxes are relatively uncertain and had not been measured until recently. So the different sources of Cno neutrinos had not been measured until recently. But they have been measured now by the Borg-Cno experiment, and that was a big sensation that this was impossible. The Borg-Cno experiment could measure the Cno neutrinos in this range of interest with energies of just below an MeV. So this red curve would have been the signal in the Borg-Cno detector, the recoil of electrons hit by these neutrinos, whereas the background is that line up here, this background. So this was a real question of being able to see that signal against that background. And so it was a triumph of background reduction techniques in this detector. The main background being withness decay, which comes from lead in the detector, and we stabilize, for example, by thermal insulation of the detector. So this was now published in Nature, and is one of the greatest achievements of this detector, which, however, now has reached the end of its life after 20 years, is now being decommissioned in the Gran Sasso laboratory. So, among others, Borg-Cno has reestablished solar neutrino spectroscopy. It has measured the solar neutrino flux over a big range of energies, which, among other things, has taught us the survival probability of neutrinos as a function of energy, which depends on the matter background in the sun. So it has actually really tested that the survival probability is a function of energy, and that tells us that the matter effect, the MSW effect, the neutrino refraction in a background medium is a real effect, which is the best proof of this by Borg-Cno. So that indeed neutrinos, the propagation of neutrinos is not only determined by the masses and the mixing, but also by the background medium. This is kind of maybe obvious, it's done particle physics, but on the other hand, here it's really glaringly obvious. So this was a Nature cover story a year ago or so, and it was a real sensation, but also in a way the end of Borg-Cno. However, the sun emits neutrinos by other sources as well. Usually we think about these solar neutrinos as being produced by nuclear reactions. However, in every star, and this is more important even for other stars, for heavier stars, neutrinos are made by so-called thermal processes, such as, for example, scattering of photons or electrons emitting neutrino pairs, the so-called photoproduction, or particularly interesting, the plasmon decay, where photon can decay into a neutrino pair through a loop of real electrons in the medium. And so this plasmon decay is a major source of neutrinos in all sorts of stars, especially like dwarfs and red giants. So that's a process that would not even exist in vacuum, but only in medium. It's a particularly interesting process. So thermal neutrinos are made by all these processes in all stars, including the sun. Now, in the case of the sun, these would have KeV energies, kiloelectron energies, have not been measured. Nevertheless, the spectrum is very interesting and can be calculated. So here's the calculation by our group a little while ago in the PhD thesis of Edoardo Vitaliano. And what you're seeing here is the spectrum of thermal neutrinos from the sun in the KeV range as against the longitude tail of the pp neutrinos, the nuclear neutrinos from the sun. So they stick above the nuclear neutrinos. or to show this in a plot like this, which you may want to use in yourself whenever you think about the neutrinos at Earth. What's showing here what we call the grand unified neutrino spectrum at Earth. The neutrinos from all sources providing a neutrino flux at Earth. There are, of course, the cosmic neutrinos, the Big Bang neutrinos, so to speak. Then there are the hydrogen atmospheric neutrinos, the hydrogen neutrinos from the universe, cosmic ray neutrinos. And then there are the solar nuclear neutrinos, and here in this KV range in between, there are these solar thermal neutrinos filling the gap between the solar nuclear neutrinos and the cosmic neutrino background. So there had always been this gap in all the previous plots, and here there are the solar thermal neutrinos. Reactive neutrinos are in the middle, and we will later talk about the diffuse supernova neutrino background, which lives here between the solar and atmospheric neutrinos, and is the dominant neutrino flux somewhere in this 10 to 30 MeV range. And these are the neutrinos from all supernova in the universe. And we'll talk about those later, but you can make a mental note already. So this is the grand unified neutrino spectrum, which you may want to consider here. Now, I said the neutrinos in the sun from the inner part of the sun have kilo electron volt temperatures. Why is that? Why is the temperature in the sun around a kilo electron volt and not a mega electron volt or an electron volt or just some other? What sets the scale? Why is it that number? So the answer to that question is actually interesting and relies on what one calls the Virial Theorem, which says that the typical kinetic energy of a particle in equilibrium is approximately -1/2 the potential energy. So if we talk about, if you approximate the sun as a homogeneous sphere consisting, let's say, only of hydrogen, of protons, and because of the mass and radius of the sun given here, then the gravitational potential of a proton near the center of this of that sphere would be -3.2 keV, just using Newton's law. And then the thermal velocity distribution gives us that the kinetic energy should be 3/2 K Boltzmann T. From this, one concludes that temperature in the sun should be around a kilo electron volt, which is very close to what one finds in the standard solar model. So you see, the properties of the sun deep inside are not some mysterious thing coming out from some complicated numerical model of the sun or something. It's based on a very simple physical argument, but can estimate that scale very easily. Right. So this is very similar to the Virial Theorem, which I just mentioned. Is very similar to how we estimate, for example, the dark matter content of galaxy clusters, which is one of the big or historically important ways of discovering dark matter. If you have a gravitational bound system of galaxies, here the Cno cluster, then we know that all these galaxies move at certain speeds, which we can measure with their redshifts. And so based on the speeds of these galaxies, of the velocities, one can conclude backward through the Virial Theorem what must be the approximate mass of the system, and from there one can estimate the total mass and conclude, like Zwicky did, for example, a long time ago, and others, that there should be a large amount of dark matter. So this Virial Theorem is a very powerful tool to understand self-gravitating systems. So once you've understood the Virial Theorem in these various situations, you have understood half of the questions that arise in self-gravitating systems, such as stars or galaxy clusters. Okay, what's next? Yeah, here I just show a few examples of the properties of the sun as a function of radius. So the sun, the temperature is around a KV in the middle and then falls off. The sun has helium in the middle, and you see the helium fraction in the middle is already 0.60 something. And so it means the sun is around halfway through its life. It's about 4.6 billion years old. So once the helium in the center, once the hydrogen is burned out of the center, it's all helium, then it'll do something else, and it has various profiles of these other elements, carbon, and nitrogen. Okay. So let's think about something else now. Now we've talked about the sun as a source of neutrinos. Let's now talk about the sun as a source for axions. Now this is a very old story. Directly when the decay axion had been proposed in 1978, these authors and others said these axions have to couple to two photons, so we can produce axions in the sun by this what's called Primakov process, where photon in the sun scattering on some charged particle gets converted into an axion, which people also called a light Higgs or Higlet in those days. And so actually calculating this was part of the PhD thesis of Rocky Kolb, the cosmologist who you may know from as a textbook author, for example. A little bit later, a few years later, the Pichet-Quinn axion had been excluded, but the invisible axions with a much larger Pichet-Quinn scale had been proposed. And so for invisible axions with a much smaller mass, actually the screening effects in this medium are of crucial importance, because the forward divergence of this Coulomb process had to be regulated by something. It is the screening effects in the medium. And actually doing this was part of my own PhD thesis a long time ago. So I'm very proud that this work is still used today after so many years. Okay. Now, how do we look for solar axions? So testing axions with stars directly. One of the ideas goes back to Pierre Secchi with this classic paper, which proposed the main techniques to search for axions that are still used today. The idea was that axions by this two photon vertex can be converted to photons in a strong magnetic field. Of course, this is used in many experiments today to search for galactic axions, the dark matter axions. But we're not talking about those in this lecture today, because we talk about stars, not the dark matter of the universe. However, in the sun, we get axions from the Primakov process. They fly to us over 8 minutes to the Earth. And then if you have a magnet, then a strong magnet, the axions going through them, could then convert to X-rays, with X-ray energies come from the solar interior, and we can see them with an X-ray detector. And so the basic idea is that the large coherence length of this conversion process kind of compensates for the weak interaction, the feeble interaction of axions, and this way one can get a significant conversion rate despite the very feeble interaction of the axions. And so one can predict the precise spectrum depending on the production energy and do this experiments. But this has been done by in a long sequence of events. So the idea is to point a magnet at the sun and look for X-rays. That's a public outreach picture made by Sebastian Baum. It was first done in 1992 in an experiment in Brookhaven, and later in Tokyo. So this telescope is just a big magnet in a vacuum tube. It's actually in the basement of the University of Tokyo, downtown Tokyo. And you can follow the sun and get a larger exposure by just following the sun. And the biggest experiment ever was of that type was the CAST experiment at CERN, where this long 10-meter long LHC test magnet was used and mounted and could follow the sun for a few hours per day, and reached a significant limit on the axion photon coupling constant. Actually, there's a nice movie of this on YouTube. I will try to link on this, although I'm not sure how good the quality will be through my limited upload speed. Yeah, probably the movie quality is not so very good for you, but you can click on it later too. But you see how the magnet can follow the sun and be used as a pointing telescope to look for axions from the sun. It is really fantastic experiment. It was a fantastic experiment, but of course now it's all not of course, but now it's been shut down by the end of last year. So that's been the end of CAST. But it's not the end of solar axion searches. There's a little point about this which I wanted to make, which I find also a little bit intriguing. You should point the magnet at the sun to see the axions, but one has to be very careful to point it in the right position, because if you look at the sun in photons, you see the visual sun near horizon, for example, just by the refraction of the Earth's atmosphere, the sun is actually lifted. So when the sun just touches the horizon, in real life, it's already below the horizon by about 1 solar diameter. So if you want to look for axions, you point at where the sun really is and not where you see it to be. It's kind of an intriguing point. In any case, these axion helioscopes are in a building and you have to calculate the position of the sun. But pointing at the sun is in this sense a little bit more trivial. I was always worried a little bit if CAST had been pointing in the wrong position in that sense, but I was assured, no, this point had been included in the calculation of the position.
Excuse me?
Pardon me? Yes?
Yeah, I have one question. Could you go to the slide, the previous slide? One more. Yeah, here you show this on the bottom left corner, you show a plot. And for the axion electron coupling, you have spikes.
Here?
A lot of spikes. Yeah.
Yeah. Okay.
But not in the case of Primakov case. So what is the origin of these spikes?
The spikes are so in the sun, the atoms, the sun is mostly a plasma. You have hydrogen, helium, carbon, iron, and all these things. But the heavier nuclei, especially iron, and are not fully ionized. So one has process. Wait, okay. Let me go back a few more slides. Here, so one has processes such as these called what they called de-excitation of. So instead of a neutral bearing axion, or the recombination is called a free bound. So an electron jumps to bound state, or you have a bound transition, and so that's how you get these lines.
I see. Okay.
This was done by Javier Redondo a while ago. He calculated this flux with the spikes. But these cannot be resolved in the detector. And anyway, when you look at the generic axion photon coupling, this doesn't play such a big role. And actually, the astrophysical bound on the axion electron coupling from other stars is so restrictive that in the sun, this is not a truly important contribution. Whereas Primakov, based on the axion photon coupling, is very interesting for the sun. Okay. So I mean, so yeah.
Okay, thank you.
I mean, I was actually wondering if for the photon coupling there could also be some spikes, but no one has quite investigated the question. But it would be a small correction, I think, for the overall picture. Okay. Now, so we talked about the cast, and now we talked about the future. So in the space of axion mass and axion photon coupling strengthens parameter space, the real axions would live on that diagonal line. The QZ axion would live on the diagonal line somewhere. And so CAST has kind of about that region here, but hasn't touched very much of the real axion parameter space, because that's very, very difficult. Because once the mass turns on, this conversion probability turns off, because the oscillation length between axions and photons becomes shorter than the magnet, so you lose coherence and lose conversion probability. But the next project is this called YAXO, which is this huge experiment. Here is a person for comparison. It's like CAST, but much bigger magnets, much bigger cross section, much better detection techniques, etc., etc. And that is the goal of that community. But meanwhile, a project called Baby YAXO is a smaller one, a steerable telescope that kind is being built at DAISY. It's all being built, so this is not just a project. It's a real. I mean, it's a real project, and the first parts are already at DAISY. It should take up operation maybe in 2024. So not in the not too distant future. And then one could cover the parameter space here in a region which is not really excluded by anything else. So there's a real discovery potential for QC axions. Of course, most people may pay more attention to the attempt to detect axion dark matter directly, but the solar axion technique is also a window, a real window, a possible discovery window for axions, a window that has not yet been closed by anything else. So there's a real discovery potential using solar using the sun as a particle source. Of course, this idea of conversion of photons to axions the other way around is also used in a variety of other approaches. For example, a magnetic white dwarf could produce axions in its interior, and then going through the B field of a magnetic white dwarf could convert to photons again. And there are some limits from this idea, which I'm not going to discuss in detail, but the idea is obvious, but the details are, of course, a lot of work. Another idea is to use the same idea as with cast in the sky, but by using, instead of the axions from the sun, the axions from all past supernova, which form an isotropic background in the Earth. And instead of the cast magnet, use the galactic B field. Instead of the X-ray detector, use the Fermilab satellite gamma ray detector. And then using all these background axions, one would get a picture like this, where in the center of the galaxy, where the B fields are strongest, one would get this bright, shining gamma rays from this conversion. Then we can get certain limits by this method, which are in that case worse than other limits. So there's another idea of using this magnetic conversion idea. Yet another idea is to shine gamma rays to the universe, because it has been claimed that gamma rays go deeper in the universe than they should be. Gamma rays in the universe are damped by pair production. So gamma rays from a distant source can form E plus E minus pairs on background photons. So we cannot look very deep in the universe in the form of high energy gamma rays. But there seemed to be a greater penetration of photons in the universe. And one idea was, if in the B fields, in the intergalactic B fields or the galactic B fields, photons convert to axions back to photons, they could bridge this effect, and so photons would propagate further in the universe than they would be able otherwise. And so there were some ideas that this might explain for some range of parameters this transparency of the universe in the form of axion photon conversion. But again, that's not our topic here, because we're talking about stars. Well, maybe the source of the hydrogen gamma rays is a bit of a star, but nevertheless, it's not our main topic here. Yet another idea that has caught on recently is the idea of looking for axion dark matter through this B field conversion process. So this idea was that dark matter axions in the galaxy, which have maybe microelectron-volt masses at typical velocities of 10⁻³ the speed of light, are accreted by a pulsar, a neutron star with a strong B field, and in that B field convert to photons that would be radio photons. So you would get a very narrow line of radio photons that can be picked up by radio telescopes. So this is a sort of complicated process that requires a lot of understanding of detail. How do the axions move through the B field? A lot of effort has been put into this recently. It was first proposed by Pshukov and Popov a few years ago, and since that time, many papers have appeared, especially recently, doing this in practice. So there's the most recent paper and some other also recent ones, where you see as a function of axion mass and coupling constant, really dark matter would be somewhere here. If axions were dark matter, you would expect a signal somewhere down here. And this technique so far has been sensitive, sort of up here, so still kind of far away from a real detection. But nevertheless, with more data, future radio telescopes, this may be improvable to a point where it might actually reveal axion dark matter. So that's another intriguing approach to looking for dark matter axions involving stars. Okay, now let's close that topic of magnetic field conversion and solar axions, and let's turn to other arguments which are a little more interesting from the astrophysical perspective and use stars themselves as a detector for axion emission. So that's a topic which I myself like quite a bit. So the idea is when a star goes through this cycle from forming like something like a sun, a red giant, white dwarf, what can you learn from that sequence of events about axions and other particles? So let's do a little of basics first, very briefly only, and sort of briefly flash the equation of stellar structure. one can find in any textbook. Basically, stars, if they're not dynamic in a more stationary state, are ruled by three equations. One is the equation of hydrostatic equilibrium, basically saying that pressure at every radius should balance the gravitational pull. So the pressure in the star has to basically balance the pull of gravity. That's kind of trivial and cast into the equation. The second is energy conservation. The luminosity streaming out of the star at every radius, the energy streaming through the star has to correspond to the energy lost or gained at that radius by nuclear reactions or by neutrino losses. It's just energy conservation at every radius. It's also kind of trivial. And finally, the equation of energy transfer, which says the luminosity driven outward is driven diffusively by the gradient of temperature. That's also relatively simple. A temperature gradient drives a diffusive flux of energy, which is carried by photons usually, or by electrons, and proportional to something called the opacity, or the inverse of the opacity, or rather proportional to the mean free path. So all one has to solve is these three equations to understand stellar structure. And energy is transported by different means. It's usually transported by radiation, by photons, through diffusion of photons or diffusion of electrons, and that's called conduction, or by convection. The medium can bubble, it can be like a boiling pot. In the sun, it's such this our sun happens to be stable from inside to near the surface. Only the outer edge is convective, whereas smaller stars have a deeper convective surface, and bigger stars have a convective core inside, are relatively stable outside. So that's called a Kippenhahn plot, where as a function of mass, one can see the convective or radiatively stable regions here. So that's just some background. And so let's also look at the question of self-regulated nuclear burning. A main sequence star like our sun burns hydrogen in its center, and its temperature is such that the Virial Theorem rules gives us the temperature inside. Now, what happens if that stable configuration would contract a little bit? Well, if it were to contract a little bit, it would heat. It would increase nuclear burning, would increase the pressure, would expand. So that's how it's stable against this. On the other hand, if there were a little bit of extra cooling, by axions, for example, it would lose a little of pressure, so it would contract. The contraction would lead to heating. It would again increase the nuclear burning rate. So this how this nuclear burning is self-regulated and stable. So that the sun is a self-regulated nuclear power reactor, nuclear fusion reactor. And so what this means is that hydrogen burning always happens at a nearly fixed temperature of around a keV. So the gravitational potential must be nearly fixed for that to happen. But that means that the gravitational potential is proportional to the mass, in inverse proportional to radius. Stars of that type, like our sun, must have a radius proportional to the mass. So if the mass is larger, the radius must be larger in a linear way, more or less. It also tells us if we were to emit axions and had some energy loss, this would not make the sun more colder inside. Quite on the contrary, it would make it a little bit hotter, so that it would produce more energy per unit time and make up for the loss of axions. So it's a little bit counterintuitive that cooling in quotation marks the solar or stellar interior actually leads to heating and make it hotter and make it lose more energy. Okay. And a little bit about nuclear reactions. So stars produce energy by nuclear fusion. And so here I show you the nuclear energy as a function of mass number. Most nuclear energy is gained by fusing protons to helium. One gains about 7 MeV per nucleon, and then forming carbon oxygen, you gain a little more, and all the way to iron. One gains a little bit more of energy, but beyond iron, you lose energy by trying to fuse particles. So iron is the most tightly bound nucleus, right? And so stars, by the normal fusion, go all the way to iron, but not beyond. Another interesting point about nuclear fusion. For fusion to happen, two nuclei have to approach each other, get very close to each other, but they're repelled by their Coulomb repulsion. And so nuclear fusion is in star very slow because the reaction rate is small, but because they are repelled. They have to tunnel through this Coulomb barrier by what's called Gamow tunneling. So they call the Gamow peak, where only the fastest nuclei can actually fuse. And so it's a very narrow range of energies, much higher than typical temperatures that can actually fuse. So this tunnel is ruled by what's called the Sommerfeld parameter involving the charges of the two fusing particles. And so for the past 20 years or so, one has been able in the laboratory to actually measure these cross sections at these very low energies in this kilo electron volt range. And so these are now experimentally established, not just extrapolated. But what this means is that this nuclear fusion is a very steep function of temperature. So hydrogen burning, for example, which happens in the sun, proceeds by the pp chains at a typical temperature of 10 to 7 Kelvin, or about around keV. Helium burning, on the other hand, where helium is fused to form carbon, goes through what's called the triple alpha reaction. The problem is here that there's no stable nucleus with mass number 8. So combining two heliums to something stable is not possible. One has to combine 3 of them to form carbon, or 4 of them to form oxygen. And because you need to combine 3 of them, it's especially temperature dependent. It happens at around 10 keV temperatures typically. And carbon burning, then it happens about 100 keV. So the main message is that these nuclear burning phases happen at very different temperatures and have to be in very different locations. Both things cannot happen in the same place, because in the same place, if one had this temperature, hydrogen burning would be explosive. So hydrogen burning, helium burning, and so on can only happen in different places in the star, typically always at the same temperature for the same process, but at very different densities. Now this observation explains a lot about stellar structure that we're getting to next. So if we begin with a hydrogen burning star like our sun, then we can ask what happens when the hydrogen burning has stopped, when we've used all the hydrogen in the center. Now the answer is that the star makes a transition to this configuration, to to shell configuration. This is kind of non-trivial, but that's what stars do. So after that, one has a helium burning core in the center and the hydrogen burning shell outside, with the temperature here would be this 10 keV, and here would be like 1 keV. So in different places, these very different temperatures. So that follows from the previous logic that different types of burnings can only happen in different places in the same star. Now, if a star goes through more and more burning cycles, one can make this whole table where there's hydrogen burning, helium burning, carbon burning, etc., etc. You get more and more burning shells of different types, and so the temperature in the center goes up to 300 keV for the silicon burning, the last phase before a star becomes a supernova, actually. And another interesting point is that stars up to carbon burning lose most of the energy actually in photons. They become ever brighter because they become ever hotter. But only for neon burning and beyond, thermal neutrinos become the main loss of energy. And for this last burning phase, silicon burning, which lasts only for a week or so, then the neutrino energy loss are about 10 to 6 times the photon energy losses. So these stars already dominantly lose energy dominantly in neutrinos of these hundreds of keV types. Okay, so that is what a star will do, and if it goes through all these burning phases. Okay, now let's turn, however, to this other configuration, to this white dwarf configuration. If the star, like a Loma star, has gone through its burning cycle, it forms a white dwarf. Now, white dwarf is a star which is governed by a different logic. The white dwarf is not supported by thermal pressure, so this whole logic that we had discussed before is not applicable. A white dwarf is supported by electron degeneracy pressure. It can be, even if there's 0 temperature, it is still stable because electrons are degenerate and their pressure holds up the star. So since pressure is proportional to momentum density times velocity, you can go through it, and it's mostly proportional to the Fermi velocity of the electrons. The firm momentum is was the largest momentum available in this degenerate medium. And so the pressure, if you go to the numbers, should be proportional to a certain power of mass and radius. And so if you have hydrostatic equilibrium, one can go through this, but eventually arises in a situation that the radius is inversely proportional to the mass. It's that famous inverse mass radius relationship for degenerate configurations. So for a mass roughly half the solar mass, as for typical white dwarfs, the radius would be around 10,000 kilometers around the size of the Earth. So a solar mass in that configuration is about the size of the Earth. Now, of course, if the mass gets even larger, then the electrons become relativistic. Once electrons become relativistic, then the velocity is the speed of light and no longer proportional to anything else. It's just a number, which means the pressure is actually smaller. And so then it can no longer be supported by electron-intensity pressure. And that is the famous Chandrasekhar mass limit, which Chandrasekhar derived in the 1920s, where he combined basically quantum mechanics with relativity and was first not believed. But in any case, he came forth with this argument and tells us that a star supported by degeneracy pressure has a maximum value, which, depending on the exact electron concentration, is around 1.5 solar masses. Now, here's another little illustration of white dwarfs. What you're seeing here is this point that if you add mass to a degenerate configuration like a white dwarf, adding mass makes it more massive but smaller. And if you add too much mass, it collapses or cannot exist. Okay, so that's the famous white dwarf physics. Okay, now how can we use all of these things to learn about particles? Now, one way to do this is to use a galactic globular cluster, where we can see many of these things very directly with our naked eyes almost. A galactic globular cluster is like something like this. It's a collection of 1 million stars, which are in a gravitationally bound system. The galaxy has about 150 to 200 such globular clusters. But the key point is if we put these stars in a different picture and sort them by surface temperature, or essentially and by brightness, we get this very characteristic picture called a Herdstrom-Russell diagram or color magnitude diagram, where we see the very characteristic pattern, which tells a lot about elementary particles. And I'll explain now how that works. So the globular cluster, again, slightly schematically looks like this. The stars arranged by color and brightness, surface color and brightness, is something like this. So the stars here are the main sequence stars, like our sun. So here are the stars of different mass and therefore different size. More mass means bigger size and greater brightness. The stars up here are no longer there because these are the stars which would have bigger masses that would have burned out already within the age of the universe, within Hubble time. And so the globular cluster, which has no gas, it does not form new stars because all the gas has been blown out by supernova explosions. So therefore we see here at the main sequence turnoff the largest mass that has survived since the formation of the globular cluster for Hubble time. The main sequence turnoff here tells us the age of a globular cluster. In any case, the stars up here on the so-called red giant branch, here the giant stars are the stars which have a burnt out hydrogen in the center and a helium core. Now these low mass stars cannot immediately ignite helium, so they have basically at the center a degenerate helium core, which is where's my pointer? Which is essentially a white dwarf. So that helium core is the size of the Earth, but has about, for example, half the size of the solar mass. It burns hydrogen around this. So the more mass in the helium core, the smaller it gets, and the hotter that shell becomes, the brighter it becomes. So we see here stars of different core mass. And finally, it ignites helium, and then it becomes what's called a horizontal branch star. Amazingly, it becomes dimmer. The reason is as helium ignites, it becomes nuclear active, it expands, by a huge factor. So the density here is 10 to 6 grams per cubic centimeter. Here's 10 to 4 grams per cubic centimeter. It's much bigger, and so it becomes colder and dimmer inside. And so these horizontal branch stars are much dimmer and live somewhere in that region here. But now, once the helium has burned out in the center, we get an asymptotic giant branch where the center is again now a carbon-oxygen white dwarf. And again, it cannot ignite immediately. So it again goes up the red giant branch called asymptotic giant branch and does the same thing again until carbon oxygen is ignited, but often doesn't even get to that place, but rather now becomes so bright that it blows off its envelope, becomes a planetary nebula, and loses all the mass here and becomes essentially a carbon oxygen white dwarf. And then we find them stars back down here as the white dwarfs, which are much dimmer because they're so small, they're very dim, they don't have much surface air to radiate, but they are fairly hot. So these are the white dwarfs down here. So that explains the structure of this Herdstrom-Russell diagram of a globular cluster. We can really identify stars in the different phases of evolution. Now, how can we learn about elementary particles? Well, one point is very easy. The particle cooling, if you have axion cooling, for example, in this region here, then this helium ignition is delayed. Helium ignites even later, and so the red giant branch extends to even brighter stars. It ignites helium at a greater density, and that's an old argument. So here I'm showing you a recent study by these authors where they looked at 46 globular clusters of the galaxy and lined them all up. So they've all been lined up at their horizontal branch, more or less. You see that the brightness at the tip is always the same. So you see that this picture is really very true that I just showed. It's always the same picture for every globular cluster. It's always that. Of course, depending on how many stars there are, it's more or less complete and more or less statistically significant. But you also see that same picture that there's the horizontal branch somewhere and the tip of the red giant branch up here. And this picture would change by axion cooling. In some old paper, we studied this explicitly and just said if we have the main energy loss is plasmon decay there, and if we switch it on and off by hand in a computer code without physical motivation, then we can change the core mass helium ignition and the brightness at the tip of the red giant branch, depending on how much neutrino losses we have. If one cranks up neutrino losses artificially to a larger value, you get a brighter red giant branch. So the brightest red giant here again, an example from recent literature, where we just see the red giant branch. So here are the red giants along here, for example, in the globular cluster 47 tuck. And here are the asymptotic giants. And so here's the brightest red giant. And how bright that is gives us a measure of this non-standard energy losses in that globular cluster, for example. Now, of course, one has to do this statistically significantly for many globular clusters. So a very recent study is by Chandrasekhar et al. And in fact, they have an even more recent study, which is not yet published. So I can't really show the more recent results, which are similar, but more slightly more restrictive. What you're seeing here is for these 22 globular clusters which they used, the brightness as a function of metal content, from which it slightly depends, and the prediction is somewhere along here, and the measurement very close. And on the other, including axion losses on that level, which would correspond to this Xeno 1 ton anomaly, is completely excluded by such arguments, and one gets a certain limit on the axion electron coupling constant, which corresponds to something like 6 or so millielectron volt, depending on details for the DFSC axions and such. Now we have made a slightly different approach to that same problem, and there's an interesting connection which I want to tell you about. Now the tip of the red giant branch shows up also in not just globular clusters, but also in all stellar populations. Here, for example, is a distant galaxy, the galaxy called NGZ 4258, which you may never have heard about, but it's important in the context of the so-called Hubble tension problem, or in the context of determining the distance scale of the universe. So in that galaxy, one can see one can measure the brightness distribution of stars in that star field, for example, here. One gets a picture like this. Every dot is a star. So as a function of color a little bit, you get the brightness of the stars. You see this discontinuity here by the blue line. You're seeing the same thing several times by different methods. One can now find this discontinuity with different statistical methods and identify precisely the point of the giant branch, the tip of the giant branch. So this discontinuity in the mass, in the brightness distribution, tells us how bright is the tip of the giant branch. And since that galaxy has what's called a water megamaser in it that allows what I call a geometric distance determination, one can, in this way, in a very good way, find an absolute calibration of the brightness of the red giant branch, which is independent of the globular clusters used by this other group before. But the very interesting situation is that this tip of the giant branch is used as one rung in the cosmic distance ladder. You may have heard of the so-called Hubble tension, which consists of the situation that the Hubble constant, which gives us the scale in the universe, has today different values. One is derived from the Planck satellite, from the cosmic background radiation, together with the cosmological standard model. It gives something like 67 in the usual units for the, here's my point here, in the usual units for the Hubble constant, whereas the so-called Cepheid method using stars and supernova 1a, etc., cosmic distance ladder gives a much larger value, about 73, and this discrepancy recently was claimed to be, I think, as much as 5 sigma. But if I use instead of Cepheids, this tip of the giant branch, but it's somewhere in the middle, so there's a tension between these different methods, which is very intriguing. I'm just flashing this as a connection to a cosmological topic, even though that's not the topic of this lecture here. But you see the tip of the giant branch is useful for other purposes as well, not just for constraining axions and other particles. Okay, so our take on this was like this, that we use, for example, this NGZ water maser brightness calibration, the latest theoretical models, and putting this together, we find, again, similar limits on the axion-electron coupling constant, or, for example, neutrino dipole moments, which are much more restrictive than, for example, the laboratory bounds. So these, again, these results together exclude by a very large margin that the Cno 1 ton anomaly could be explained by solar axions. Okay, there are other ways of using these globular clusters. Let me speed up a little bit. So there could be particle emission from the horizontal branch. That would imply that the horizontal branch stars burn faster. You get fewer horizontal branch stars compared to other burning phases here. And using this statistical method, the number of horizontal branch stars compared to other stars can be used to constrain, for example, the axion-photon coupling constant. And this was done a long time ago, and most recently by these authors. And they find a bound on the axion-photon coupling constant, which is comparable to the cast limit, coincidentally. Okay, and then yet another idea uses the white dwarfs that could also produce particles that would cool faster. So white dwarf cooling could again constrain these parameters. And so white dwarf cooling can be seen in a plot like this, where one shows the number of white dwarfs in the solar neighborhood in the local environment as a function of brightness. So white dwarfs cool pretty fast when they are hot, but then they cool ever slowly. So they build up at small luminosities, at dimmer ones. So it has more dim ones than bright ones. So that explains that slope here. But that slope essentially tells us how fast are white dwarfs cooling. And the usual neutrino cooling by plasma loss gives a fairly good result. But so if one were to put an axion loss on top, that curve would be deformed. And these authors find if they put in too much axion cooling, this cooling curve gets so much deformed that it's no longer compatible with the data. On the other hand, they think a little bit of extra cooling would actually be required to get the best fit of this cooling curve. So there has been a little bit this idea floating around that there might be a little hint for extra cooling from these white dwarfs. But for the moment, one cannot really prove that this is true. But again, the bound again is in the same ballpark as the previous one from the red giant branch at around 10 milli-electron volt for the DFSC axions. Another idea uses white dwarfs that are variable. The variability or the change of the period is also a measure of the cooling speed, but this is getting very complicated. I'm not going to get into this in any detail. If you want to know more about this, you have to maybe go back to these papers. So I'm just flashing in the end. Very, very coincidentally, only a few days ago, there has been a big review. It's part of physics laboratories, and so you can look up these different ideas. And essentially, the point is that the globular cluster bound by us and the other groups are fairly restrictive and somewhat more restricted than what you get from the white dwarf luminosity function, and probably in contradiction with this interpretation of the cooling hint, but not completely. So there's still room for having a little bit of extra cooling in white dwarfs, other than by standard neutrinos. So much for
Excuse me.
Yes, please.
Yeah, in the previous slide, here, for example, there is a number GE equal to 5.66 plus minus 0.57. Yeah, that's almost 10 sigma measurement, 10 sigma effect, right?
Well, yes,
roughly, but yeah, but it's not consistent with the other measurements, right?
Exactly, it's not consistent, right? And this comes from these variable. It's like, I think this star, it's a very white dwarf, a pulsating white dwarf, it's called, where the cooling speed is measured by its change of period, which is a very different measurement. So here, this green range gives us the measured change of the white dwarf pulsation period, measured over many years. And the prediction would be something like this here, the theory prediction. And so if one takes it at face value, one would say that the energy loss of that star should be something like this, if interpreted in terms of axions. But of course, it can also be interpreted in terms of a systematic error that we do not understand. So here's another of these stars, but this situation is very different. Another of these unstable dwarfs. So yeah, if we take this star by itself and take all the stated uncertainties at face value, that is a very strong detection of an additional cooling channel. I agree. And so it's very intriguing. On the other hand, all these other bounds are much more restrictive. And so, yes, I don't think there's at the moment any clear way of interpreting these things. On that, I'm not an expert on the theory of pulsating stars. So what exactly could be going wrong here is a very important question. But this also tells you that once you find such a signature, then one should be very, I mean, in a way, it's much easier to believe a limit than a detection, right? And to interpret this as a truly new cooling channel, if it were true, it wouldn't have to be axions, it could be something else. But what exactly is going on in that star, I cannot tell you, and I think these authors also do not know.
Thank you.
But if you want to know more, read this review. So that's why they call them lights and shadows, because they're good and bad things, or clear or less clear results. But it's a very intriguing situation, of course, but has been there for a long time. Okay, so I just meant to say that this has not been applied only to axions, but also dark photons, for example, where the stellar limits give us some interesting constraints. These look like different stars. This is due because there's a resonance effect going on for dark photons. I just mentioned this very briefly because it's interesting. The idea is that if we have dark photons, they can actually mix with so-called longitudinal plasmons. So the plasma oscillation in a star have the usual photon-like propagation mode, the so-called longitudinal mode, where just the electrons oscillate against the protons, where the oscillation frequency is almost independent of wave number. And so there's also a crossing place where the dispersion relation of a dark photon crosses with that of the longitudinal plasmons. Then you get a resonant conversion between the two, and that explains these resonant peaks in the bounds for the different stars at different conditions. It's kind of a very, very interesting phenomena for dark photons. I'm just flashing this. It's an interesting application of dispersion, photon dispersion in medium compared to, in that case, dark matter, dark photon dispersion or free dispersion of dark photons in the medium. Okay, so much for ordinary stars. Let me now turn to my second topic, which is the heavier stars, which don't follow this upper branch here, but which follow this lower branch, where the star has a sufficient large mass to become a red supergiant, and finally becomes a supernova. So my second part of my talk will focus a lot on neutrinos and particles from supernova explosions. So what is a supernova? So I've shown this picture a lot, which is the so-called Crab Nebula. So the Crab Nebula is one of astronomy's most often shown picture, and what it shows is the remnant, the exploded remnant of the historical supernova of the year 1054, which was reported in these Chinese records here in those days. So that supernova was observed by Chinese and reported by Chinese astronomers, even though there was no report in Europe in that case. It was sometimes called the Chinese supernova, and it left behind the Crab pulsar, the compact pulsar object, which is here shown as a composite image of X-ray images. So this pulsar shines most of X-rays and stirs up the stellar medium around it. It's called a plerion. So one can see that pulsar in the center of that nebula. So this illustrates the two things we get in the core collapse. We get a compact object, in that case a pulsar, and this extended nebula from the explosion, where most of the star has been blown away by the explosion. So what physically happens is the following: that the end state of a star, it has gone through all the burning cycles. It has developed an iron core surrounded by different burning shells, as explained earlier. And that iron core, as we explained earlier, cannot ignite any more nuclear burning. It's the most tightly bound nucleus. You cannot ignite iron because you cannot gain nuclear energy by igniting iron. So as you add more mass to that iron core, it becomes smaller, as we explained earlier, becomes becomes smaller and more massive, and eventually has to collapse when it has reached its Chandrasekhar limit. Then it collapses down to nuclear density, where the equation of state stiffens. So actually, after that, it's supported by nucleon degeneracy pressure, and forms an object of essentially nuclear density in the center. And then the implosion is suddenly halted to form a shock wave that moves outward and is supposed to explode the star. And after that, it has formed this dense object from which neutrinos escape by diffusion. Neutrinos of all flavors. So looking at that final picture, we have this object of a few tens of kilometers size, which is so dense and so hot that even neutrinos cannot stream freely. So a supernova core is the only astrophysical environment, except for the early universe. Neutrinos cannot stream freely, but are scattering around and reach thermal equilibrium. And so they diffuse out slowly meaning over a few seconds, whereas the free streaming time would be much, much faster. And so the whole gravitational binding energy of that object of maybe 20% of its mass all get out in the form of neutrinos. Just a huge amount of neutrinos coming out. About 1% of this total energy goes into the kinetic energy of the explosion, and about 1% goes into photons that sort of still outshines the host galaxy. So for a few seconds, the neutrino luminosity of that star is so large that while it lasts, it outshines the entire rest of the visible universe. It's a very huge energy, a hugely energetic event, as you can guess from these numbers. So that's why supernova neutrinos are so interesting. So on the other hand, a supernova does not explode very easily on the computer. And the reason is that the shock wave that forms moves outward, but it forms inside this iron core. So as it moves out, it actually transfers energy to the iron core and dissociates the iron. It basically is dissipated and runs dead, and it basically stalls. So usually on a numerical simulation, that shockwave doesn't explode the supernova. So there's always this question, how does supernova actually explode? Now the answer, the neutrinos play a key role again, because while the shockwave sits there in a fixed radius of maybe 150 kilometers, neutrinos stream outward while material is streaming inward. And the neutrinos, while they stream outward, still scatter occasionally, still deposit energy behind the shockwave. This energy deposition puts more hydrodynamical pressure behind the shockwave and makes it gain energy and finally explode after all. This is called the delayed explosion mechanism, or Bethe-Wilson mechanism, who discovered this in the early 1980s, a long time ago. So neutrinos play a key role in exploding supernova. Now, this is it has been recognized recently that this is not just a simple picture, but supernova are intrinsically three-dimensional objects. So they develop convection in these layers. They develop coherent sloshing oscillations called the Sasi mode. So they are very active hydrodynamical events. I'll try to show you a recent picture that you can find, a movie that you can find later on YouTube, because my upload speed is not very fast. It will not look very good maybe, but I'll try anyway. So that is a so this is from the Princeton group. They put this on YouTube and you can look it up later. What you're seeing is how now it's coming, how it's accreting material and then develops these convective plumes and convects and rolls over. I mean, you can look it up later. You'll see a smoother version of the movie, but you more or less can guess probably what you should be seeing. You get these convective plumes. So that's more or less the picture of how a supernova evolves. Wait a sec. Okay, now we go back to my slides. So you can roughly see how a supernova is supposed to evolve nowadays. Here from the Garcia group is a similar picture, just still images. You can see how it can slosh back and forth and develop these convective plumes. So that's how much you picture supernova explosion. That's why it's not very spherically symmetric. Indeed, supernova 1987A was very asymmetric, and that caused this idea of supernova not being a very symmetric affair. So it's a very 3D, very 3D event. But let's return to the simplest picture again to explain the supernova explosion physics. So here, what I'm showing again is a schematic picture as a function of time in a logarithmic scale. So one has this iron core collapsing on this sub-second time scale and forming ultimately this 10-kilometer neutron star. Meanwhile, a shockwave forms deep inside, moves out, stalls for some hundreds of milliseconds, and then goes again off as the shockwave has been revived by neutrino emission. So there's the accretion phase where the shockwave stalls the fixed radius for a long time, while matter is still streaming in and powers neutrino emission. So that's a rough picture of how things evolve, and that reflects in the neutrino signal that we expect. So there's this early neutrino burst for the first first tens of milliseconds, where the outer layers deleptonize, the outer layers, the electrons convert to electron neutrinos, whereas this quick burst of electron neutrinos, also called the deleptonization burst, or prompt neutrino burst that happens for the first few tens of milliseconds. Then one has this accretion phase for a few hundred milliseconds, where stuff falls in, one gets lots of electron neutrinos and the so-called X-neutrinos. And then one has this long cooling tail where where the energies go down and down and down, and the luminosity slowly goes down on the time scale of a few, maybe 10 seconds or so. Okay.
Well, excuse me?
Yes, yeah.
Yes, so what is the new X here? Is it mu or
what is new X? I come to that in just a moment.
Yes, okay.
Just a moment. Sometimes, however, you have no explosion at all, and rather the whole thing collapses to a black hole. It must do this in some cases because we know there are black holes. So in some fraction of cases, one must form black holes rather than neutron star. And then one still gets a lot of neutrinos, in fact, hotter ones, because until the black hole reforms and it recollapses to a black hole, one gets a lot of neutrino emission, which are even hotter than you would have otherwise assumed. Okay, so now we get to this question of what is an X-neutrino. Yes, so that's a very bizarre thing in what the supernova people do. So in a supernova, one has no trapped muon or tau lepton number, but one has trapped electron lepton number. And so one has electrons with a mass of a half an electron MeV and temperatures of tens of mega electron volts. So electrons are basically massless in the supernova core, comparatively speaking, whereas tau and muon neutrinos not. And so in supernova simulations, one usually treats the electron neutrinos and the electron antineutrinos as different things because charged current reactions are very different for them. And everything else is called an X-neutrino, whether it's a mu bar, tau bar. So in supernova neutrino simulations, one often has this what's called three species neutrino transport, where one uses these three species, so to speak, as representing all of the neutrinos. Now, this is an approximation, clearly, but this was maybe good enough until recently, but this is still done in most supernova simulations because the neutrino transport is numerically the most expensive part of supernova simulations because one has to solve the Boltzmann collision equation. Deep inside the supernova core, neutrinos diffuse, and one can use a diffusion approach. Far outside the stream freely, so one has to mimic in a supernova simulation, especially the part between the inner part and outer part when neutrinos change between diffusion and free streaming. So that intermediate part is the most crucial one, where neutrinos also deposit energy in the behind the shock wave. So the intermediate region is the most interesting one for supernova physics, but cannot be treated by any simple approximation. So it has to solve numerically the full Boltzmann collision equation, and that is what's numerically difficult. The hydrodynamical part of the supernova simulation is kind of the cheap part. And so everything has to be optimized to get the neutrino transport done in a way that's actually numerically doable. So that's why this approximation has been used. And of course, flavor oscillations have never been implemented in supernova simulations. On the other hand, it has recently been recognized, even though it's kind of obvious, but it's only recently become very clear that muons nevertheless exist in the supernova core, even though as the supernova collapses, it traps all the neutrinos and has a large number of electron number trapped inside, which has to come out over a few seconds. It has no muon number trapped. On the other hand, as muon neutrinos diffuse out, one builds up a chemical potential of muon neutrinos, and after a second or so, one has actually almost as many muons as electrons in the supernova core, maybe a quarter as many. So the muon abundance in the supernova core or neutron star is not that small, even though it has been neglected in the past in most simulations. But to do this properly, one has to implement a six-species neutrino transport, which from particle physics perspective would be the most natural thing to do. You have E and mu and tau neutrinos and the antiparticles, which is 6 species, which all have different opacities, different behavior, and they all should be implemented separately. But this is only done now in special studies by the Garchin group. So here they show that the muons actually help a little bit with the explosion, which is shown here. But let me not spend too much time on this question. Yeah, let me briefly talk about this other question about the possible collapse of supernovas to black holes. I mean, the question is, or in the olden days, people said, yeah, how do supernova explode? But today we have to ask both questions. How is it that some supernova explode, others don't? Because there should be the so-called failed supernova, which do not explode, but rather form black holes. So the word failed supernova is maybe a bad word, because they actually succeed in forming a black hole, which we need. So one way of actually measuring how often that might happen is to actually observe many supergiants that might become a supernova, which are the progenitors of supernova. So in this project, one observes about 1 million supergiants in close by galaxies, which have a lifetime of about 1 million years until they become supernova. And so one would expect around 1 supernova per year among 1 million supergiants. And so ideas with this telescope, one looks at these several times per year. One visits each of these stars and checks if it's still there. And so if a star disappears without forming a supernova, it must have collapsed to a black hole. And so there has been 2 candidates. Meanwhile, at that point, there was 1 candidate where a star, which has been there in these previous images, has disappeared in these different observational bands. So the star has gone, has disappeared. So that's probably a star that has formed a black hole instead of a neutron star, instead of a supernova explosion. So based on the latest results from that group, they say, based on these 1 or 2 candidates, the fraction of black hole forming supernova maybe a quarter. So that is in agreement with some theorists phenomenologically say that maybe a quarter of all core collapses may turn into a black hole. I find it very interesting that this can be studied by direct observation of these many, of 1 million stars. I think it's a very intriguing project. Okay, but let's turn to neutrino and neutrino observations. So the only one time that supernova neutrinos have been observed was the supernova 1987A, which is now 35 years ago, almost to the day. It was when this star Sandulak -69202 in the Large Magellanic Cloud, which is a little satellite galaxy around 160 light years away from the Earth. It's a little outside of our own galaxy. So that star exploded to become supernova 1987A. So that's an image before that time. It was in fact historically the first time one could associate a supernova explosion with a progenitor star that was identified on previous observations. Okay. And yeah, so here are the observations in different detectors that were active in those days. The Kamiokande detector in Japan that had been built to search for proton decay had just been refurbished to search for solar neutrinos. The IMB detector in the US, which had also been looking for proton decay but didn't find it, but also saw the supernova explosion, and the Baksan telescope then in the Soviet Union, which also claimed a signal, also maybe a lesser statistical significance. And so within clock uncertainties, all these signals were contemporaneous. Here they are aligned at the first neutrino and confirmed roughly that neutrinos would arrive over a time scale of a few seconds. So that seemed to confirm in those days the basic picture that that supernova trapped neutrinos, which then come out over a time scale of a few seconds, maybe 10 seconds out of the supernova core. The energies roughly correspond to what we expect, even though the IMB and Kamiokande energies were very different, so they're barely consistent with each other. The total energy emitted and the spectral temperature is very different. Of course, they're very bad at low energies because they are below threshold in these old detectors. But there is a common region which is consistent, corresponding roughly to what one would have predicted. So it seems within the large uncertainties of the observations, everything seems to be more or less consistent. So one interesting part of the physics result that was used, which I always have liked, is the proof that neutrinos actually are subject to gravitation, even though nobody questions that probably. So the idea here is that the neutrinos arrived several hours before the photons as expected. So the visual light curve went up roughly like this. These are the observed observations, and the neutrinos were observed a few hours earlier. And so if the transit time for neutrinos and photons is approximately the same, which is 160,000 years, within a few hours, that means they must have propagated with the same speed to that precision. On the other hand, the Shapiro time delay, which is the slowing down of signals in the gravitational potential, would be a few months in the standard physics. Because a trip from the LMC to us would be slowed down by a few months in the standard GR picture. And so neutrinos and photons must respond to gravity the same way within about 10 to -3. So that proves that neutrinos respond to gravity the same way as photons, for whatever that's worth. But it's an interesting observational point. Okay. The main particle physics constraints derived from the supernova neutrinos were based on the so-called cooling argument, where a supernova core, the neutrinos diffuse out over seconds, also emits axions, which can escape freely from the core because they are more feebly interacting and unscattering. They just stream away freely, and so they would short the neutrino burst, and so the late time signal would be the most sensitive observable. And this argument was used for many different particles, especially for axions, and constrains their interaction rate. So this traditional argument has been reviewed by many people recently for various reasons. So there's a review of the old arguments, and then there were quite a number of recent arguments which mostly were about improved nuclear physics for the emission rate of the axions, and also point out that pionic processes, pionic scattering of protons might create axions and find an increased emission rate. But at the end of the day, the limits are roughly similar to what one had before. So one finds that the axion mass, if one translates the bounds of axion mass up to about 10 milli-electron volts for some class of axion models. On the other hand, these authors say, wow, maybe we haven't even seen supernova neutrinos, because one big embarrassment for all of this has been that the neutron star, the core of the supernova core, has never been observed in supernova 1987A. So where is that neutron? Where is that pulsar? Where is the neutron star? So this has never been observed. Curiously, however, very recently, the ALMA observations observing in the sub-millimeter range have observed the inner part of the supernova remnant and found that hot blob in that region here, which is interpreted as being heated by the neutron star behind it. So the idea is that it's hidden behind that cloud and blob, and that there actually is a neutron star there and not a black hole. So probably a neutron star formed as expected by the neutrino observations, but the neutron star has never been found in that supernova. That's an interesting point that one should keep in mind. Okay, let me go on. So here are the summary of the limits on axions, or the opportunities for axions from stars. So if we look at the energy scale for axions, going from the Planck scale down to smaller massive Pitcher-Quinn scale of the axion mass, this range, all these astrophysical limits exclude something for masses below above 10 milli-electron volts or so. Super radiance, which I'm not covering here, excludes some very small range of axion masses down here. You must have heard about this in a previous lecture. In between, one can still look for axions by this conversion of dark matter axions, by this magnetic conversion, and YAXO can look in this range for axions. So there, and of course, there are huge opportunities for detection, including, as you know, in Korea, there are important dark matter search experiments for axionic dark matter, but I'm not covering this in my lecture here. I'm only showing what stars can do for axions here. So that's the axion summary. Okay, but there have been a number of new arguments that have been studied recently that I want to get into briefly, which is the question when we don't talk about axions, but about axion-like particles, which are not directly axions, but have a larger mass, let's say for similar interaction strength axion-like particles that couple to photons in particular, then these particles, if emitted from the supernova core, can decay into 2 photons on the way out. Now, if the decay length is very large, we just have the usual cooling. But if their decay is so fast that they decay within the progenitor star before it has exploded, they deposit energy in the progenitor star. It would help with explosion and maybe even provide too much explosion energy. On the other hand, if they mostly decay outside of that core, they may decay to photons would be picked up by a gamma ray satellite that was up there during the supernova, and it is a neutrino burst, or they could be picked up by all they could add to the cosmic gamma ray background from all past supernova. It could be picked up, for example, by the Compton X-ray telescope. Let me just go through these 3 points in order. So in supernova 1987A, there was a gamma ray satellite called the Solar Maximum mission up there, and at the time of the neutrino burst, there was no change in the counting rates of the gamma rays in different detection channels of the instrument. And so, because there was no excess count after the neutrino burst, provides limits on possible radiative decay of neutrinos or ALPS emitted from the supernova core. Another argument which we very recently proposed is that if these particles dump the energy into the mantle of the supernova core, then supernova explosion should be much more energetic. And so, to compare this reality, we should look at the lowest energy supernova explosion that exists. So there exists a class of low explosion energy, so-called subluminous type 2 plateau supernova, that have very small explosion energies. So that they give us very restrictive constraints on the possibility that too much energy might have been dumped into that supernova envelope. And so it provides us with very restrictive limits in that space of axion mass or ALP mass, the coupling constant to photons, in this range of very massive, hundreds of MeV massive particles, which in the past were not considered in such great depth, but today are considered as one possibility. Right. The third case that we looked into recently is the photoproduction of such particles in the supernova core if these particles couple to muons. So one can, in the supernova core, produce muonic bosons, which might explain the muon G-2 anomaly. So one produces these muonic bosons in the supernova core by photons, and then they could decay through this muon loop outside and produce these distant photons, produce photons at a distant distance from the supernova. And so, just going through all these arguments, we derived limits on such scalar bosons and pseudoscalar ones as well from different arguments. The diffuse gamma rays from all entire universe excludes a range of parameters for large masses in this 10 to minus 10 range in these units, or at very strong couplings, it excludes a large range of parameters up here, excluding the G-2 interpretation in terms of scalar bosons of the muon magnetic moment anomaly. So that's a range of recent results in this context. So one is using the diffuse supernova neutrino flux, or the diffuse flux of axion-like particles from all supernovae in the universe. Now that brings us to the topic of the diffuse neutrinos from all supernovae in the universe. So all core collapse supernovae in the universe produce neutrinos, and the distribution of core collapse supernova with distance is encoded in the cosmic star formation rate, which is a steeply rising function of redshift. So there was a lot more star formation in earlier times because there was a lot more gas around. And if one plots it in this way, one finds that the star formation rate, or the core collapse rate as a function of redshift, peaks at around a redshift of 1. So when the universe was approximately half its present size, is when it formed most of the core collapses, simply because there was more gas at a larger redshift. One runs out of volume. There's not very much universe at larger redshift. So basically, at this redshift of 1 is the peak, and one gets around 10 million core collapses per co-moving megaparsecs in the universe to account for cosmic neutrinos and photons and ALPS and other things. So one
excuse me.
can, yes,
Excuse me, sorry. Could you go back to the slide of muon Felix scalar boson? Yeah.
this one.
Yes. So how I missed how you exclude this muon
Yes.
Felix?
Yes, again.
Could you explain
Yes.
please?
So in the supernova core, these photons hit muons and produce these new bosons.
Yes.
Then these new bosons propagate and can decay into 2 photons through an unavoidable muon loop. So these bosons have no choice but to couple to 2 photons.
Okay,
Except
I see. So you assume this scalar couples only to the muons.
in this case, yes.
Okay, I see. Thank you.
And then these photons have various impacts on the explosion or can be detected. That is the main idea. Does that answer your question?
Yes, thank you.
Okay. So this was this idea, and of course for pseudoscalars it gives us a limit, but pseudoscalars would not be able to explain the anomaly. They would just make it worse. Right. So for such as we call muon-Philip bosons, there are all these bounds derived. They can be derived from these supernova different arguments. So let me now return to the neutrinos. One can predict the cosmic background neutrinos in from all these supernovae in the universe called the DSNB or diffuse supernova neutrino background. And so the predictions depend on the cosmic star formation rate, some detail of supernova models, and one prediction is this one here as a function of energy. And the current limits are not very far away from this, from Super Kamiokande. And so the detection of the DSNB is, one could say, just around the corner. And who will detect them? There are 2 detectors online that probably be able to do this. There's the Super Kamiokande in Japan, which has recently changed by using gadolinium, dissolving gadolinium in the water, that has just started well in 2020. And gadolinium is a good neutron capturing element, and therefore one can subtract background much more efficiently and identify the inverse beta decay by electron antineutrinos on protons. And so Super Kamiokande should be able to detect the DSNB over a few years. And the other is the Juno liquid scintillator that is being built in China. So here was the little New Year's greeting card of the Juno collaboration. I suppose in Korea you also celebrate the Lunar New Year about a month ago. So that was it's the year of the tiger now, I suppose, in Asia. In any case, so here's the scintillation detector that's being built in China and should be able to also detect the DSNB over the next few years. So here at a rate of a few events per year. So DSNB is probably the next supernova neutrinos to be discovered if all goes well with these 2 detectors. Then of course will put us in a much better position to also derive particle constraints. If we know that indeed the diffuse superneutrino background is there, then also the diffuse axion and dark photon, etc. background must be there, emitted by all of these core collapses in the universe. Let me finally turn to my last topic, which is the neutrinos from the next galactic supernova, which is of course something we've been waiting for a long time, but should happen at some point. So if the next galactic supernova happens, there are many detectors online that could do this. In particular, the most important detectors are the Super Kamiokande detector in Japan and the ice cube detector at the South Pole, and a number of smaller detectors in the world that could also get a signal. The bad news is that even with these big detectors, we cannot look far beyond our own galaxy. So our own galaxy, the Milky Way, is here, surrounded by some small satellite galaxies, including the Large Magellan Clouds. And then there's the next neighbor galaxy, the Andromeda Galaxy. at a distance, however, so large that even with super Kamiokande, one would only get a few tenths of events from a supernova in that galaxy. So we mostly have to, for a high statistics observation, we mostly have to rely on our own galaxy. Now, the supernova rate in our own galaxy is unfortunately not so large. One has various ways of determining that, from the statistics of external galaxies, from gamma rays of aluminium in the Milky Way, which is produced in supernova explosions, the historical core collapse rate that has been observed in over 1,000 years in our own galaxy. On the other hand, no core collapse in neutrinos was observed since supernova 1987A. That gives one a limit. And right. And so the idea that there could be 2 or 3 supernova per century in our galaxy, and so it's a once in a lifetime event, but still means if that rate is true, there's a 3% chance every year, but so far it hasn't happened. I mean, there's Poisson statistics. It's very unfortunate. I mean, there are some galaxies which have a large supernova rate or a low one. Our neighboring galaxy, the supernova, the Andromeda galaxy, which I showed earlier, has had the last observed supernova almost 150 years ago, the supernova 1885A. On the other hand, the so-called fireworks galaxy, which is too far away from neutrino observations, has a supernova almost every 8 years. The most recent one in the year 2017, and actually I want to show you this one just as a cultural point. This is a link to the Sky and Telescope magazine. So Sky and Telescope is a journal for amateur astronomers, and so they discovered this as a first time. So what you see here's the supernova where it's flashing. So there are 2 images overlaid, before and after the supernova, which were observed by this amateur astronomer in that night on May 19th. So here's the supernova. So I'm just showing this to illustrate in the supernova context. Even amateur astronomers do a very important job in detecting new supernova in the sky, sometimes quicker than observed by professional astronomers. That's just on the side. But in any case, our galaxy is not like this. Our galaxy is a much more lazy supernova producer, not like that galaxy, unfortunately. So we have to wait for a long time for supernova. On the other hand, if one were to happen, neutrinos would be the first thing that we would see. And so there is that supernova early warning system called SNOOS, where different neutrino detectors feed their possible observations and send an alert. You can book an alert yourself. You can go there and register and get an email or an email notification if a supernova has happened, neutrinos. That would still give one a few hours to trigger gravitational wave detectors or astronomical detectors to be on alert for observing in their other wave bands for that event. So it's a very important idea of multi-messenger neutrino astronomy. So why is IceCube a good neutrino detector? That's a confusing question, because IceCube is of course built for detecting high-energy neutrinos, not low-energy ones. However, however, the IceCube detector consists of this huge array of optical modules frozen in the Antarctic ice, as you presumably know, and each optical module picks up photons in the Antarctic ice. And so each optical module has a background current of a few hundred events per second, like a few hundred hertz background rate. But if you have 5,000 optical modules together, they have this, would get this very correlated noise from this. The Antarctic ice would shine blue and direct of photons with a supernova neutrino go through. And from this correlated noise in 5,000 optical modules, one could get a very significant neutrino signal with a very good neutrino light curve from IceCube at the South Pole. Moreover, this is a detector which has almost, I think, a 99% uptime, so it's very unlikely to miss a supernova if it happens anytime soon. This is very interesting because a supernova signal may contain very intriguing short time variations if the supernova hydrodynamically shows these instabilities, these Sarsi oscillations, this dipole oscillations of the envelope, it would modulate the neutrino signal on this few millisecond time scales. The neutrino signal would show these periodic variations over a few hundred milliseconds, and that could be observed in these neutrino detectors. So one could really detect in superkamiokande, or of course hyperkamiokande, or in ice cube in particular, one could observe these hydrodynamical instabilities and test in great detail what's happening in the supernova in such a detector. I find this a very intriguing possibility, but it requires a galactic supernova. So also, of course, such features would be smeared out by neutrino mass. If the neutrino had a mass, these features would be smeared out by time of flight effects, but the laboratory bounds and the cosmological limits on the neutrino mass are so small that this effect would not be important. Or conversely, you can say if this effect were observed, one would obtain an independent measure or constraint on neutrino masses. So that's also an interesting point. Okay, the next generation of detectors are Ice Cube Gen 2 with a lot more optical strings, the megaton class detectors, of which I hear one may also be built in Korea. But for now, I think the hyperkamiokande will be built, one of them in Japan, the Juno in China. I don't know what the exact state of Reno 50 in Korea may be, but you know probably more about this one. And of course, the Dune detector in the US. So there are many big detectors coming up. So I think if a supernova happens, many detectors are online now and will be online in the future. So I'm very optimistic that at least for the next decades, there will be a lot of observing power online to get a very detailed statistical information about the neutrino signal. And that would provide a lot more reliable and detailed information about neutrinos, of course, and of course about axions and all the other particles, because all these arguments that were done for supernova 1987A would have much greater statistical significance and could be made much more precise than one has been able to do with supernova 1987A, which is now so long ago, but it's still the only supernova neutrinos we've got to work with. Another interesting point is that these dark matter detectors, which use coherent scattering of neutrinos, so the xenon enton, for example, would also be sensitive to supernova neutrinos. It's quite intriguing that supernova neutrinos can even be seen in dark matter detectors, which are not gigantic, but just a few tons of material. And so these are kind of small, and still one can see supernova neutrinos. That is a very intriguing recent development, and of course will be another channel of possible detection. So let me in the last few minutes turn to a topic that is very complicated. And so I'm only very brief on that topic, which is the question of supernova and flavor conversion. We've already observed or noted earlier that in supernova simulations, in numerical simulations, this effect is not included at all so far. So in supernova, numerical supernova simulations, they are done as if flavor oscillations did not exist. And this is partly justified because there's that strong meta effect, which deep inside the supernova actually suppress flavor conversion. So even though the mixing angles are large, as you know, between neutrinos, between different neutrino flavors, deep inside a neutron star, the meta effect is so large that essentially neutrinos are demixed, and the electron, mu, and tau neutrinos are the interaction eigenstates are the same as the propagation eigenstates. And so nothing would be expected to happen deep inside. On the other hand, as neutrinos stream out of a supernova, there should be various flavor conversion effects that so far have only been treated on a kind of post-processing level, but eventually should be included self-consistently. So going from inside out, of course, far outside, there could be the usual MSW conversion that we have in the sun and other places, which in the sun have been observed by Cno in particular. So they must happen in supernova as well in the gradient of the envelope. So that's unavoidable. Deeper inside, however, there could be the so-called self-induced flavor conversion effect. Now, this has been noted quite a few years ago already, that neutrinos themselves are an important background for neutrino propagation, provide an important meta effect for neutrinos. So that becomes a nonlinear phenomena that causing a large number of confusing effects that may or may not be observable in the future detection. But what has kept people very busy most recently is the so-called fast flavor conversion effect, which can happen even more deeply inside, which is an effect that is due again to neutrino-neutrino refraction, but does not even depend on them having masses in mixings. There's just an instability in flavor space between neutrinos that can be triggered by a small amount of flavor violation, can maybe cause flavor equilibration even deep inside on some level. And so that's a topic of active research that I can only hint at in my lecture here. So in terms of a two-flavor picture, neutrino oscillations go by the vacuum masses, which are the usual vacuum oscillations. There's Wolfenstein's meta effect, the MSW effect that's caused by the background medium and the background electrons. And then there's this nonlinear effect caused by the background neutrinos. And that is so important because neutrinos, as they oscillate, develop a coherence between, for example, mu and electron neutrinos. And then there is this what's called off-diagonal refractive index, which can cause potentially large conversions of flavor conversion among neutrinos, because the neutrinos themselves feed back on the Hamiltonian that causes flavor conversion. And that is the essence of nonlinear flavor conversion effects. Deep inside, ignoring for the moment the self-induced oscillation, we have the normal MSW effect where neutrinos produced as a flavor eigenstate inside, come out as a mass eigenstate to the surface, depending if they're neutrinos or antineutrinos. Something produced as electron neutrino inside would come out as a third mass eigenstate, for example. Something produced deep inside as a mu eigenstate could come out as the lowest mass eigenstate, and so on. It depends on the mixing parameters and the mass ordering. And so one can do this MSW pattern for different mass orderings, and one can find between normal and inverted ordering whether Nui and bar survival probability is big or small, etc. And so this is the basic of neutrino flavor conversion. So one way of looking for this is the early neutrino burst. So I told you that early on there's this burst of electron neutrinos coming from a supernova, which is a very characteristic and feature which is almost like a standard candle. It looks the same for any modeled supernova. Everybody finds the same result. It's a very characteristic feature. It's almost like a standard candle. And so if it's observed in such a way or not, would be a measure of this MSW conversion of supernova neutrinos. And so that phase can be observed in the forthcoming Dune detector in the US, if one can observe electron neutrinos as opposed to antineutrinos. So for no oscillations, Dune will observe this big spike, or for inverted mass ordering or for normal ordering, maybe nothing at all. So depending on what one observes exactly in this Dune detector would give us a direct hint on the neutrino mass ordering, just as an example, even though this can be maybe established at other experiments at the Earth. Or we can look at the rise time of the supernova signal in Ice Cube or in Super Kamiokande, and can see how the signal goes up as a function of energy, where the Nui bar signal would go up last, whereas the others would go up more quickly because of the different flavor, because different flavor neutrinos rise with different speed. So this is another way of observing these effects. So simply turning again to the self-induced flavor conversion. so there is this effect of pairwise flavor conversion caused by neutrino refraction, where a neutrino pair can collectively convert to a flavor pair of to a pair of another flavor. And this can happen on a very short length scale or time scale deep inside the supernova. And this is called the fast flavor conversion effect, which is the subject of a very strong current research, which I'm not really being able to study here in detail. That would be a lecture in its own right. I can just flash this at you to tell you this is what's going on about supernova neutrinos, and has not been fully resolved. So it's not completely clear how to implement supernova neutrino conversion, flavor conversion in the supernova core. I mean, the effect on the supernova explosion itself should be there, but maybe not on the complete changing the picture of supernova explosions, but could still have a significant impact on the explosion mechanism and on the nucleosynthesis of different elements in the neutrino-driven wind in supernova and binary neutron star mergers. Okay, so just summarizing up that story of the self-induced flavor conversion. So I've also shown that picture. The question of neutrino interactions and the impact in supernova neutrinos has been a subject of many years of research, but still we always say the same things. Only the beginning, a lot more work has to be done. What exactly it will do and how exactly to implement that in a supernova simulation. So this is a kind of unsolved problem in supernova physics as far as its connection to particle physics is concerned. So I just show this little summary of supernova questions that were asked maybe around the time of supernova 87A that are asked today. In those days, when supernova 87A happened, we didn't even know how many neutrino flavors there were. And we didn't know about their masses, we didn't know about oscillations, and we didn't really understand how core collapse, supernova explode. All of these things are now basically answered. Today, one asks about neutrino mass limits, one asks about, we know about a lot more about neutrinos, and probably interpreting a neutrino observation of a supernova, we know all of these things about neutrinos and can use the signal to learn about the supernova and about other particles. So the picture has completely reversed since those days and today, except we still have to use the old neutrino observations to learn to do any of these things, because we don't have a galactic supernova observations just yet. So there will be many lessons to be learned. So these authors have recently summarized this in a very nice paper where they subdivide the neutrino signal of the next galactic supernova in several phases: the pre-supernova silicon burning phases, the accretion, this quick burst, the early cooling phase, the late cooling phase, and the final fallback phase. And from all of these phases, we can learn different things about neutrinos, about flavor mixing, about other particles. And so if the next galactic supernova happens and it's observed neutrinos, it will be a bonanza of information for many things in particle physics and astrophysics. So coming to my conclusion, pretty much in time after 2 hours. So what can particles and stars do for each other? Of course, there's always room for new ideas, and many new ideas have been proposed recently. There have been many recent papers on dark photons, fuzzy dark matter, axions, and so on, using new observables. And of course, we can extend and refine the existing arguments about ordinary stars and neutron stars. What I like a lot is the search for solar axions, which has a bright future, especially in the form of baby axion Yaxo, that has a real chance of turning up new particles in terms of solar axions. Likewise, searching for magnetic converted ALPS or dark matter particles can provide a real detection. So I think these points are perhaps the most interesting ones. The next galactic supernova observation, with a 3% chance every year, will be a bonanza for new information. what I really like are new theoretical developments in collective neutrino flavor evolution, even though I've just hinted at these issues for a brief moment. And of course, the next supernova neutrinos to be observed are the diffuse supernova neutrinos that I've talked about. So I think these are sort of my favorites in terms of the future. And I'm concluding with this summary. Thank you very much for your attention, and for those who've made it to the end of my talk. So if there are questions, more questions, I'm available.
Oh, thank you very much for a nice talk, like very comprehensive. And I have already asked a few questions, but regarding my last question about Munich scalar boson,
yes,
about the mu G -2. So I think your plot shows the bound up to scalar boson mass up to around 10 MeV. So suppose suppose you consider 100 MeV which Munich scalar bosons, then I guess it's not strongly constrained by astrophysics.
Yeah, our constraints don't extend to that region. So but I think in that range, one gets into the range where one has accelerator bounds
right.
So I think we stop there, because then other bounds kick in.
Okay.
But there was that open range in that regime. Of course, at yet larger masses, you can explain it. I think I'm not an expert on these bounds when they come from accelerators and colliders.
Okay.
But I think beyond that range, you get maybe more reliable or more direct constraints from colliders. Yeah.
Okay. Thank you.
Other questions?
It's been a very long talk. And you also can look up the slides later and maybe remind yourself. I think it was uploaded to the web page. Is that correct?
Yeah.
Okay, Georg?
Yes.
So I have a similar question about this muonic force.
Yes.
So you stopped at 10 MeV because, I mean, you are thinking of onshore production.
Well, we stopped at 10 MeV really for practical reasons, honestly, because at that point you can treat them as relativistic, and one doesn't have to. Everything gets a little more complicated for larger masses. That's kind of why we stopped there from a practical perspective, and because at larger masses the accelerators kick in more directly. That was our.
Well, actually, still 100 MeV is too low for accelerator source. But I mean, for instance, if it is 100 MeV,
yes.
So this the photons can be produced through off-shell coupling, and
yes.
I guess still you can get a strong bound from.
Yes. I think so too. Yeah, but we didn't do it in our paper here.
Yeah, although I don't know the exact solution, but it seems that all the parameter region explaining muonic mass of the 100 MeV would be ruled out.
I think so too, yeah, but we didn't do it in this paper.
Okay.
Ruled out by this
the off-shell coupling of the heavy scalar.
Of course, excuse me. There's of course another issue. But once you take the masses beyond around 10 MeV or so, then also the production mechanism becomes more complicated, because then you can also make them by photon fusion into these scalars, not just by the muonic photo production.
No, I mean, so you attach the bosonic field to the muon, right? And
yes.
then this bosonic field goes to 2 gamma through one loop.
Yes.
So we can, we have this, although the phi or axion-like particle are massive. This is kind of offshell process.
why is off shell?
I mean, you cannot produce a phi on shell, but we have this 2-photon production.
Why can we not produce on shell?
I mean, I don't know. I mean, it's if the system, I mean, like 400 MeV scalar.
Yes.
Probably it's too heavy to be produced inside the.
No. It would not be too heavy. In the supernova, I should find my.
Okay, good. Yeah, then right.
In the supernova core, you have a temperature about 30 MeV, so a typical energy is 100 MeV.
That's right. Then
photons.
Okay, good, very good.
The scalars coming out have a spectrum which
Okay.
of around 100 MeV, 200 MeVs or so, and of course.
Yeah. There must be enough tail of producing this.
Yeah. It's at the maximum and the tail of the thermal spectrum.
Okay, very good. I mean, then
a few hundred MeV can be produced.
Even include a few hundred MeV. I don't know.
Yeah,
okay.
You can produce a few hundred MeV, no problem. But in our detailed study, we didn't study this case. I think I remember that all the other arguments kick in at that point.
I see.
But we only sort of looked at this lower mass region because then we could treat them relativistically and didn't have to worry about many other applications. Okay. For us, it was more a question of practicality, but for sure it can be extended to high masses. Yes.
Okay. Good. Thank you.
Anything else?
Excuse me.
Yes.
I have one question.
Yes.
It's a very general question. But, in your lecture today, is there any place hierarchy of neutrinos does matter?
The mass ordering. The hierarchy do you mean the mass ordering, which is the normal or inverted ordering?
The neutrino chirality. He's asking about neutrino chirality of neutrinos.
Left-handed or right-handed chiralities of neutrinos.
Chirality of neutrinos.
Yeah, chirality of.
Sorry. I just I'm sorry.
Sorry.
No. The chirality. No, this is a very interesting question. But no, I guess the question is would be things like left-right collisions or small neutrino masses play a role. Not that I know of within standard physics, because neutrino masses are so small that left-right transitions are strongly suppressed, just like in the early universe. Also in the supernova core, even though neutrinos scatter around, to scatter from let's say into a right-handed Dirac neutrino, for example, or to scatter into an anti-neutrino in the Majorana case, the rates are much too small. On the other hand, if neutrinos had anomalous dipole moments, magnetic dipole moments, then this could happen. Of course, neutrinos have dipole moments in the standard model if they have masses, but these are very, very small. But if neutrinos had anomalous large dipole moments in beyond standard model physics, then of course it can happen that a neutrino in a magnetic field, for example, turns from an active, let's say an electron neutrino turns into an antineutrino of a different flavor. So these will be the so-called mass flavor transitions. And then yes, if I were to observe electron antineutrinos in such a situation, that could be a hint for such things. But that would be, of course, beyond standard model physics, which of course we would all like to find. Also, for example, solar neutrinos have been used to set limits on the flux of antineutrinos from the sun. The sun, of course, produces only neutrinos, not antineutrinos, and so a limit on the flux of solar antineutrinos is also a limit on such transition magnetic dipole moments, which I have not shown here, but yes, these exist. But within the standard model, the chirality has not been important. It has been questioned if in a supernova core there could be collective effects causing spin transitions, holistic conversions. by the mass term through collective effects that neutrinos could pair and so on. But in practice, it seems all the studies that have been done that these effects are extremely small, as one would naively expect, because neutrino masses, especially majority mass, are so small that once you talk about 100 MeV neutrinos, all the amplitudes are down by so many orders of magnitude. Then in practice, any of those effects are extremely small. So that's all I can say on that topic.
Dankeschön.
I have one more question. So today you did not mention about this constraint on the stellar neutrinos.
Stellar
So
neutrinos,
are there some useful constraints to the stellar neutrinos?
Well, of course,
from the
if
start?
stellar neutrinos exist, then again everything can be different in a supernova, depending on the mixing parameters, or for some neutrinos. But it is it's a very complicated subject, actually. I mean, stellar neutrinos in supernova is a very complicated subject because let's say we had a stellar neutrino of a few tens of keV mass, then one can get resonant conversion in various regions of a supernova, and the stellar neutrino can transport energy from one place to another within the supernova in a way that is very difficult to mimic analytically. On the other hand, nobody has ever implemented stellar neutrinos in a consistent way in a numerical supernova simulation. So this is a topic which I always said I don't want to touch with the stick because it's so complicated. It has so many features to it. So it's not very simple, although there have been interesting recent studies on that question. Although I also must say that I'm personally not such a very big friend of stellar neutrinos. So this is, but that's just a question of personal taste for one who wants to.
Thank you.
But stellar neutrinos, of course, depending on their parameters, could have an important impact on anywhere where neutrinos themselves are important, of course. But I told you earlier, in supernova simulations, in the standard numerical works, one has not even implemented standard flavor conversions, let alone stellar neutrino conversion. So I'm myself more interested in the question of the collective flavor conversions, which is fully standard model, which is complete standard model particle physics. Yet I find theoretically very interesting questions of collective behavior of the neutrino field in that environment. So I'm myself much more interested in that question. But of course, other people are also interested in stellar neutrinos.
Other questions? I see no more questions. So thank you for the very nice lecture.
Thanks for inviting me and having me.
Thank you very much.
And yeah, I hope you can look up the slides if you like on the indico of my talk.
Yeah, you can find the indico link in the chat window. So please check. And is it okay to upload this video to